4 days ago, on April 22nd, 2026, a team of astronomers at Western University in Canada released an image that stopped the scientific community in its tracks. It was captured by the James Webb Space Telescope, the most powerful observatory ever built, pointed at a cloud of glowing gas and dying starlight 10,000 light-years away from Earth, in the constellation Ara. The image showed something that no human instrument had ever seen in this detail before: the birthplace of Buckyballs, tiny hollow spheres made of exactly 60 carbon atoms, each one shaped like a perfect soccer ball at the molecular scale, arranged inside a dying star's outer shell, in a configuration so precise and so unexpected that the researchers who mapped it said the result was, in their own words, really fun to see. Microscopic hollow spheres arranged in the shape of a massive hollow sphere, buckyballs inside a buckyball, 10,000 light-years from Earth. And in that image, in that extraordinary geometric coincidence, lies one of the oldest and most profound questions that science has ever asked. Where did life come from? Because what these molecules are, what they carry, how they form, and how they travel across the galaxy touches the origin of every living thing that has ever existed on this planet in ways that most people have never been told. The story of Buckyballs begins not in space, but in a laboratory at Rice University in Houston, Texas, in September 1985. A team of scientists led by Harold Kroto, Richard Smalley, and Robert Curl were trying to understand how carbon behaves in the atmospheres of giant stars. They vaporized graphite with a laser inside a helium chamber and analyzed what emerged. What they found stopped them cold. The experiment kept producing an extraordinary abundance, a carbon molecule with exactly 60 atoms, no more, no fewer, that appeared with 40 times the frequency of any similar molecule. For days, the team struggled to understand what shape could make a 60-atom carbon molecule so uniquely stable, so resistant to breaking apart under conditions that destroyed everything else they produced. The answer came from an architectural sketch. Smalley, working with a paper model late one night, realized that the molecule's stability arose from its geometry: 12 pentagonal faces and 20 hexagonal faces, arranged in a perfect sphere, exactly like the geodesic domes designed by American architect Buckminster Fuller. They named the molecule Buckminster fullerene, immediately shortened to Buckyball. The carbon-carbon bonds holding it together are among the strongest chemical bonds in nature. The hollow interior of the cage can trap other atoms and molecules inside without reacting with them. The structure is so geometrically perfect that it is simultaneously one of the most beautiful and one of the most chemically resilient things that nature produces. In 1996, Kroto, Smalley, and Curl were awarded the Nobel Prize in Chemistry for the discovery. From the moment they were first synthesized, Kroto predicted that buckyballs would be found in space. Carbon is the fourth most abundant element in the universe, and it is endlessly creative in how it assembles itself. From the simple carbon monoxide molecules detected in interstellar clouds, to the complex aromatic hydrocarbons floating in stellar nurseries, to the even larger carbon cage structures that Kroto believed the universe would produce in the high-temperature environments around stars. But for 25 years after 1985, nobody could prove he was right. The instruments available to astronomers were not sensitive enough to detect the specific infrared light signatures that buckyballs produce. They were too faint, too diffuse, hiding inside the glow of stellar environments that produce dozens of overlapping spectral signals. Then, in 2010, Professor Jan Kami at Western University in Ontario pointed NASA's Spitzer Space Telescope at a planetary nebula, a cloud of gas and dust expelled by a dying star, called TC1, located approximately 6,500 kilometers, light-years away in the constellation Ara. The Spitzer telescope, operating in infrared wavelengths invisible to the human eye, detected spectral signatures at wavelengths of 7.0, 8.5, 17.4, and 18.9 micrometers, a unique combination that matched Buckminster fullerene and nothing else. Kami and his team published their discovery in the journal Science in 2010. Buckyballs existed in space. Kroto had been right, and the scientific community immediately began to understand what that meant. Planetary nebulae are not random clouds of gas. They are the recycling engines of the universe. When a star, roughly the size of our sun, exhausts its nuclear fuel, after billions of years of fusing hydrogen into helium and heavier elements at its core, it does not explode as a supernova the way more massive stars do. Instead, it swells into a red giant, its outer layers expanding outward over thousands of years until they drift away from the core entirely, forming an expanding shell of gas and dust that glows with the ultraviolet light of the hot white dwarf left behind at the center. These expanding shells, the planetary nebulae, contain everything the star synthesized during its lifetime. Carbon, oxygen, nitrogen, silicon, sulfur, all the heavier elements built up layer by layer through billions of years of nuclear fusion, now being released into the interstellar medium. the space between stars, where they mix, drift, and eventually become the raw material from which new stars and new planets form. When Cammie found Buckyballs inside a planetary nebula in 2010, he had found them at the exact location where the universe packages its chemistry for delivery to the next generation of worlds. And Buckyballs, as molecular containers capable of trapping other molecules inside their hollow cages, are among the most significant possible delivery vehicles that chemistry could produce. The question of how Buckyballs form inside planetary nebulae was, for 15 years after the 2010 discovery, one of the most persistent mysteries in astrochemistry. The problem was chemical. Planetary nebulae are hydrogen-rich environments. For every single carbon atom in the gas cloud, there are roughly 10,000 hydrogen atoms. In the laboratory, Buckyballs are made by blasting pure carbon together with no hydrogen present. Hydrogen is chemically reactive with carbon in ways that should prevent the 60-carbon cage from assembling. As Jacob Bernal, an astrobiology doctoral student at the University of Arizona who studied this problem, described it, if you have a box of balls, and for every 10,000 hydrogen balls you have one carbon, and you keep shaking them, how likely is it that you get 60 carbons to stick together? It's very unlikely. And yet the Buckyballs were there. The spectral signatures from TC1 were unambiguous. The universe was making Buckyballs in an environment where chemistry said it should not be able to. That contradiction drove nearly a decade of investigation. The answer, when it finally emerged from work at the University of Arizona, involved a completely different starting material than anyone had considered. Dying stars like the one inside TC1 produce enormous quantities of silicon carbide during their red giant phase, a compound where carbon and silicon bond together in the extreme temperatures of the stellar atmosphere. This silicon carbide condenses into tiny dust grains as the star's outer layers cool during expansion. When these grains are then hit by the powerful ultraviolet radiation from the hot white dwarf at the nebula's center, combined with the shock waves from the expanding gas shell and the bombardment of high-energy particles, the silicon is progressively stripped away from the surface of the grains. What remains is carbon, pure carbon, in the form of graphite sheets, just a few atoms thick. And those graphite sheets, once liberated from the silicon carbide substrate, do exactly what the 1985 laboratory experiment showed graphite sheets do when heated to extreme temperatures. They curve, they fold, they shed unstable carbon chains from their edges through a process researchers call shrink, wrapping, and they collapse into the most stable geometric configuration carbon can achieve at 60 atoms, the Buckyball, born not from pure carbon in a vacuum, but from the death of silicon carbide dust grains under the assault of ultraviolet light and stellar shock waves in a hydrogen-rich nebula. The universe had found a way to make them that the laboratory had never imagined. Now, in April 2026, the James Webb Space Telescope has looked at TC1 for the first time, the same nebula where Buckyballs were first confirmed in space 16 years ago, and what it has revealed goes far beyond what any instrument before it could show. The JWST's mid-infrared instrument, called MIRI, captured TC1 across 9 infrared filters simultaneously, spanning wavelengths from 5.6 to 25.5 micrometers, producing the first detailed mid-infrared image of this planetary nebula ever made. The image is extraordinary in its detail, delicate rays extending outward from the nebula's edge, wispy filaments threading through the glowing gas, concentric shells of material at different temperatures, hotter gas glowing blue in the processed image, cooler material traced in red. And at the heart of the nebula, an ethereal structure that resembles an upside-down question mark, a feature whose origin nobody on the research team can currently explain, whether it is the product of complex gas flow dynamics, magnetic field, interactions, or the gravitational influence of an unseen companion star that has shaped the nebula's expansion asymmetrically. But the scientific finding that is already changing how researchers think about Buckyball formation came from the mapping, not the imaging. PhD candidate Morgan Giese led the painstaking analysis of where, precisely, the Buckyballs are located throughout the TC1 dataset. The result was surprising in a way that nobody had anticipated. The Buckyballs are not scattered randomly through the nebula. They are not concentrated at the edges where the ultraviolet radiation is strongest. They are not spread throughout the central gas cloud. They are concentrated in a single thin spherical shell immediately surrounding the central white dwarf, a layer of molecular material sitting at a specific distance from the dead star, defined by specific temperature and radiation conditions that apparently favor the assembly and stability of the 60-carbon cage structure. As Giese described it, the microscopic hollow spheres are arranged in the shape of one giant hollow sphere. Buckyballs, organizing themselves into the shape of a larger buckyball. The geometry is either a remarkable coincidence or a clue to something fundamental about the physical conditions that produce these molecules. conditions defined by distance from a radiation source, by temperature, by the density of the surrounding gas. Understanding why the buckyballs are arranged this way is now one of the central questions driving the next phase of the research, with multiple scientific papers from the TC1 JWST dataset currently in preparation. The significance of all of this for the question of life's origin is impossible to separate from the chemistry. Carbon is the backbone of every organic molecule that biology uses, every amino acid, every protein, every strand of DNA, every lipid membrane, every sugar. Life as it exists on Earth is fundamentally a carbon chemistry phenomenon, and the question of where the carbon and carbon-based molecules on the early Earth came from has been debated since the origin of life became a scientific question in the 20th century. One of the most compelling hypotheses, supported by a growing body of evidence from meteorite analysis, interstellar chemistry, and now planetary nebula observations, is that the organic chemistry of life did not begin on Earth. It began in space. It was built piece by piece in the environments around dying stars, packaged into dust grains and molecular cages, incorporated into the asteroids and comets that swept through the early solar system, and delivered to the surface of the young Earth during the period of heavy bombardment roughly 4 billion years ago. Buckyballs, found in meteorites recovered on Earth, are part of that delivery record. They have been identified in the Allende meteorite in Shungite, a carbon-rich rock from Karelia in Russia over 2 billion years old, and in fulgurites formed by lightning strikes. Their presence in terrestrial geological material confirms that they made the journey from space to Earth, and their extraordinary chemical stability means they could have survived that journey intact, carrying whatever molecular cargo was trapped inside their cages when they formed. Professor Jan Kami, speaking about the significance of buckyballs in a statement accompanying the JWST findings, described them as a type of polycyclic aromatic hydrocarbon, a class of organic compounds that he calls ingredients of life. He noted that buckyballs are found not just in dying stars like the one at the center of Tiki-1, but in young stars, in interstellar clouds, and in meteorites, essentially everywhere in the universe where carbon chemistry is active, but not very frequently, and that their sporadic presence is part of the mystery. Postdoctoral researcher Dries van de Putte, who is studying fullerene emission and other nebulae beyond Tiki-1, framed the question that the entire field is now working toward answering. Did the buckyballs found in space form the same way they form in laboratories on Earth, or by a completely different process? Because the answer to that question determines how universal the chemistry of buckyballs is. How many? Dying stars across the Milky Way are producing these molecular cages, loading them with trapped atoms and molecules, and dispersing them into the interstellar medium to eventually rain down on forming worlds around new stars. Princeton University's Marissa Weichman, an assistant professor of chemistry whose lab has been designing a new spectrometer specifically to measure the light absorption of fullerenes in the laboratory for comparison with space telescope data, described the broader scientific context with directness. These molecules, she said, are the prebiotic origins of life, the seeds of molecules that start life. That is why her team is looking at them. The NSF-funded project at Princeton is building reference data for the James Webb Space Telescope and for future infrared observatories, providing the laboratory absorption spectra that astronomers need to identify not just C60, but the larger family of fullerene-like molecules, the ones that are currently producing unidentified spectral lines in telescope data, lines that cannot be matched to any known molecule, lines that suggest the universe contains carbon cage structures beyond C60 that science has not yet characterized. Each one of those unidentified lines is potentially a new molecular species, a new piece of the prebiotic chemistry that connects dying stars to living worlds. What the James Webb Space Telescope has done in returning to TC1 is give scientists their first real data set. Not just an image, not just a detection, but a full chemical map of a buckyball birthplace. PhD candidate Charmy Bhatt, who worked on the analysis, described what the dataset means in terms that capture the scale of what has changed. She said that structures which were completely invisible before are now laid out with stunning clarity. The shells, the rays, the fine details in the outer halo, and crucially, through the integral field unit spectroscopy that JWST's MIRI provides, everything visible in the image can now be connected directly to the chemistry and physics happening at each point throughout the nebula. The temperature, the density, the gas motions, the molecular identities. Every point in the image is simultaneously a picture and a chemical analysis. The entire nebula has become a laboratory. And in that laboratory, the oldest question of all, where did life's chemistry come from, is being approached with instruments precise enough and data rich enough that the answers, when they come, will be built on evidence rather than inference. The buckyballs in TC1 have been waiting 10,000 light years away for 16 years since their discovery, carrying their message in the dust of a dying star. The James Webb Space Telescope has finally started reading it.